Hey everyone. In your workbook, it seems like we're in a different chapter, and we are, but this is still part of the exponents and logs unit, so we're continuing on. Today we're going to look at exponential equations, solving them. We actually have already looked at solving exponential equations, and that's of this type. So just for a little practice, let's say we go through these two and we practice solving these. These are exponential because the variable is in the exponent. Now when you look at the bases on either side, you'll notice 2 and 4, those could both be written as base 2. So you're going to want to do that. And so I'll just walk you through that one. So 4 is going to be replaced with 2 squared. X is on the outside. Okay. And then we want to simplify the exponents, power over power, you multiply them. Okay, and this was our goal really at this step, is to have one power equals another power. The bases are the same, therefore the exponents will now equal each other. And then we solve for x by getting x on one side, subtract x from both sides, and you would get x equals 3. And there we go. Why don't you guys try B? A little bit trickier. On the right hand side, make sure you have one power before you let the exponents equal each other. Okay, so pause your video and then we'll check back and see how you did. Okay, hopefully you got x equals 1. And as I mentioned, this is just a review from a previous lesson. So if for some reason you had trouble with that, please check with me in class, okay? Now, that was fine for when we can get the bases the same, but let's say we have something like 2 to the x equals 50. Well, if we tried to get 50 as some exponent of 2, you'll notice that there's no nice number that can do that. So we could test this out and see if we could guess. It might be between, let's see, 50, 2 to the 5 is 32, and 50 is bigger than that, and then 2 to the 6 is 64, and 50 is smaller than that. So I think our answer needs to be between 5 and 6 because of that, the exponents here. Okay, we could estimate the solution, but that's probably good enough. But what we're going to learn on the next page is what to do when you have those situations where you can't get the bases the same. And that is exactly what they're showing here. We're going to actually log both sides, base 10, because that's what your calculator does, so that's a good base to put it in. And what you do is you go log of the left-hand side, 2 to the x, equals log of the right-hand side, log 50. And then we use our power rule from logarithms, whereas if we have something in the exponent on something we're logging, that can move down front. Okay, and then next step would be to divide both sides by log 2 to get x by itself. And so x would equal log 50 divided by log 2, and that would be our exact solution answer. And if we wanted to the nearest tenth, we would put that in the calculator. Let's bring that up a minute. Boom, boom, boom. Okay. And we should get, after you put that in your calculator, log 50 divided by log 2, 5.6. And they want it to the nearest tenth, so we'd stop there, 5.6. There we go. Let's practice with some more equations and some little bit more difficult ones on the next page. Okay, solve the following equations, expressing the solution as an exact value, so no calculators there, in the form log m divided by log n. And then, second part, 3 decimal places, so that's when we'll put it in the calculator. Okay, now A is very similar to what we just did, so why don't you guys try that one, pause your video, and we'll check back in a minute. Okay, so when you look at this, you notice we can't get the bases the same. 12 is not 4 to some exponent, at least not a nice exponent. So we log both sides. Base 10 we chose to do on the log. We could choose actually any base on our log, but because the calculator does base 10, we choose that. Then our exponent on the 4 can come down front now that there's a log. And then we divide both sides by log 4, and we get, as an exact value, log 12 divided by log 4. Or throw it in the calculator, we get x equals 1.792. All right, let's take a look at B. Okay, so our power is here. That's where our variable x is, which means we kind of want to get rid of that plus 4, okay? That's not really doing us any good. So let's subtract 4 from both sides, and then we'd have 8 to the x equals 36. Okay, now check and see if you can get your bases the same. Can I write 36 as 8 to some exponent? And that would be a no. So then you go ahead and log both sides, get x by itself, okay? So you might as well pause your video and go ahead and do that, and then we'll check back. Okay, so did everybody get exact value? Log 36 divided by log 8, and to the 3 decimals, 1.723. Okay, good job. Okay, C, a little bit different, a little more difficult. You'll notice that we have x on both sides in the exponent. Okay, so first check, can our bases be made the same, 6 and 3? No, they can't. Remember, it has to be a power, right? And 6 is not 3 to some exponent, not a nice number anyways. So we are going to jump in and take the log of both sides. Okay. And you'll notice I'm not writing the base on the log, and that's because base 10 is assumed to be there when you don't write it. Okay, now that we've got that, the exponent, we're using our power rule for logarithms. Our exponent, oh, that is a funny 3, will come down front of the log, being multiplied by the log. Okay, now, do not do what I just did on the right-hand side here. Notice I didn't write 2x minus 1 in brackets, so what this essentially means when I don't write brackets is only the log 3 is being multiplied by the 1, not the 2x as well. So please make sure you put brackets around that 2x minus 1, okay? Now, where's Waldo? Okay, we have an x on this side, and we have an x stuck inside brackets on the right-hand side. We need to free this x up. So we are going to multiply the log 3 through. Okay, now remember, don't mess with what's inside the log, okay? You can't do that. Let's just write the left-hand side down again. So really that 2x gets written in front of the log, as in multiplying by the log, minus, and then 1, or you don't have to write that, minus log 3. Good, now check, where's Waldo again? We have x on this side and x on that side. Those x terms need to be on the same side, so, and the number on the other side. So we're going to actually take and subtract 2x log 3 from both sides. Okay, and then you'll probably notice, please don't try and subtract those because they're not the same terms. This is 3x log 6, this one is 2x log 3, not the same. So you cannot collect them. But here's how we're going to end up isolating x. We are going to factor x out because it is common between these two terms. When you divide it out of the first term, you'll be left with 3 log 6. Okay, divide it out, minus the second term, 2 log 3, equals negative log 3 still on the right-hand side. Okay, now that we have x times all of that, we can get rid of all of that by dividing by it. So we would then have negative log 3 on the right-hand side divided by all of that ugliness. And believe it or not, we're not done yet. Okay, so we have isolated x. The only thing is they said that we should write it in log m divided by log n form. So let's take a look at that. Well, okay, the numerator looks pretty good, except there's no negative sign in front, but we'll take care of that. In the denominator, we want to combine these logs. So we're going to use our logarithm laws again, except we can't combine them until these little coefficients go back into the exponents, right? So that's from lesson 6 and 7 in the last unit. Okay, so we're going to, oh, and you know what we're going to do with that negative 3, since we're doing this with that? Or sorry, negative 1, I mean. That negative 1 in front of the log on top is going to go back into the exponent too. Okay, so let's get rid of that negative sign. So we'll have log 3 to the negative 1 over log 6 to the 3 minus log 3 squared. Okay, that's looking good. Now we can combine our two logs in the denominator. Oh, and that 3 to the negative 1 I'm just going to write as 1/3, right? And then we're subtracting 2 logs in the denominator, so that's the same as dividing within 1 log. So that becomes, let's see, 6 cubed, I want to say 216, I'm guessing in my head, divided by 9. And then we can divide 9 into 216, and we get log 24. And there we go. Now if you compare it to the form they want, we have that. m would be 1/3, and the n value would be 24. Awesome. Okay, so if we put that in the calculator now, let's just bring up the calculator. So we'd have log 1/3 and the bracket on that divided by log 24. Let's see what we get. So we get negative, they want it 3 decimal places, negative 0.34, and then we'd round that up to a 6. So negative 0.346. Good. Okay. All right. Oh, D. Yes. Make sure you write small n d. Okay. So part D. Yes. This looks a lot more complicated. So can we get the bases the same? No, of course not. 3 and 7. Forget it. Okay. So we are going to log both sides. Lots of brackets going on here. Okay, log base 10 basically on both sides. Good. Now, unlike the last question where we moved the exponents down, like we can do it on the right-hand side. That one's fine. That would become x log 7. However, on the left-hand side, the x minus 2 exponent is only on the 3. So you can't move that down in front of the log because it's not applying to everything inside the log. So we're going to have to use another logarithm law, and that's if you're multiplying within a log, it's the same as adding 2 separate logs. Okay, and there we go. Now that exponent of x minus 2 can move down in front of log 3. So we're going to do that. Make sure you put brackets around it. Do I sound like I'm nagging? Good. Okay, now we're going to multiply the log 3 through. Okay, and the reason why we're doing that is to get that x out of the brackets, because we're not going to be able to isolate it with it stuck inside brackets. Alrighty, there we go. Now, where is x? It is in this term and this term. Trust me, it helps to underline those. So those two terms need to be on one side, and since I've got the numbers on the same side already, I'm going to subtract the x log 3 to the other side. Okay, so we'd have, how did that become a log 3? We have log 2 still on this side, minus 2 log 3 on the left-hand side, equals x log 7 minus, now we're subtracting the x log 3 to the right-hand side. Good. Okay, so actually, why don't you guys take it from here? You should be able to finish this up. So keep going with how we did the last one, and we'll see if we get the same answer. Make sure you combine it into log m divided by log n form, okay? So pause your video, please. Okay, how did we do? Did everyone get this as your exact value and this is your decimal? All right, good job. Check over, make sure you've got the same work, and we should be good to go. Okay, simple cases. We'll skip example 2. We'll just stick to the one way to do it. Okay, in example 3, Stats Canada, population growing, average annual rate. They give you the equation. Okay, sorry, this is hard to read. And they tell you n is the number of years, and a known population is the beginning population, p naught, and then predicting it after a p amount of population after a certain amount of time. Okay, so they tell you if the Canadian population beginning in 2001 was 30 million, well, that sounds like p subscript 0, the initial. Estimate in which year the Canadian population will reach 50 million, so that's our p, assuming the same average annual rate of growth. Okay, so estimate the year, that means we're looking for n. Okay, so let's sub everything into our equation and then use some logarithms to solve that, okay? So pause your video and then we'll check back. Okay, how'd we do? We put 50 in for p, 30 in for p naught. You wanted to isolate your power first by dividing by 30. That makes the question a whole lot easier. And then you'd have the log of 5/3, that reduced, equals the log of 1.01 to the n. N comes down, divide by log 1.01, we should get 51.3. But they asked for in which year compared to the year 2001. So we go 2001 plus 50, oh, I don't know why I wrote 53 years, sorry. Plus 51 years would put you in the year 2051. All right, good job. Let's take a look at the next page. I think we'll skip example 4, and example 5 you already know how to do. You just put one side in y1 and one side in y2, and your intersection points are your answers, okay? So you should be fine with that. See you the next time.